Hello, dear friends. Let's solve summer 2025 41 9702 paper. Yeah, first question, define gravitational potential at a point. I think we know the answer. So it's the work done. It's a work done moving in unit mass from infinity to that point. Okay. Next, Mars is a planet that may be considered to be an isolated uniform sphere of radius 3.4 into 10 power 6 meter. A satellite of mass 122 kg is in orbit around Mars at a constant height of 1.7 into 10 power 6 meter above the surface of the planet. The height of the orbit is increased to 6.8 into 10 power 6 meter above the surface. This increase the gravitational potential energy of the satellite by 5.1 into 10 power 8 joule, so that the mass of the Mars is 6.4 into 10 power 23. Okay, see, the idea is from H1 to H2 they are moving, so there is an increase in potential energy. That increase in potential energy is 5.1 into 10 power 8. So the formula for increase in potential energy is this one, G capital M, that's mass of the Mars, small m, that's mass of the satellite. H1 is height from the center of the mass. H2 is height from the second position from the center of mass. So actually, if you do not know where does this formula come from, I'll add the derivation then. Okay. Now remember, H1 and H2 are from the center, not from the surface. The height is given from the surface, so we should add. So if we rewrite this formula for capital M, we get this. And then maybe this is a little complicated, so let's just work out for H1, 1 by H1 minus 1 by H2. So I just took 10 power 6 out factor, and then H1 from the center is radius plus height from the surface. So radius is 3.4 into 10 power 6 plus height 1.7 into 10 power 6 minus H2 is again 3.4 radius plus 6.8 into 10 power 6. So if we factor out 10 power 6, then we get 1 by H1 minus 1 by H2 is 9.8 into 10 power minus 8 meter inverse we should get. Okay, so now we have this value. Let's substitute. We know the G value 6.7 into 10 power minus 11. We know the change in gravitational potential energy, that's also given us 5.1 into 10 power 8 joule. So we'll substitute everything, then we will get 6.37 into 10 power 23 kg. Okay, so let's explain how do we get this formula. Change in potential energy is 1 by H1 minus 1 by H2. Okay, we know the electric potential is minus Gm by H. Let's say there are 2 points, 2 electric potential, EP1 and EP2. So difference in potential energy is EP2 minus EP1, right? So we will have minus Gmm by H2 minus Gm by H1. So it's minus of minus, so it will become plus. So the H1 will come first and then the H2 will come next. So if we take out Gm and M common, then we will have 1 by H1 minus 1 by H2. So it's just, we just factor out Gmm. Yeah. Okay. Nice. Most people make mistakes that they don't count the distance from the center. They just use the distance from the surface, so they'll end up getting a wrong answer. Okay, done. Calculate the gravitational potential phi at the surface of Mars. Give a unit with your answer. Okay, we know the phi formula is minus Gm by R. So again, minus G is 6.67 into 10 power minus 11. Mass of the satellite just now we found out as 6.4 into 10 power 23. So radius is 3.4 into 10 power 6. So if we substitute everything, I have put with the unit Newton meter square kilogram power minus 2 for a gravitational constant that you can refer from your page 1, and kilogram and meter downstairs. So it will be minus 1.26 minus from the formula into 10 power 7, and we have meter square, and in denominator we have meter, so we will remain with meter. Kilogram power minus 2 and kilogram, so we will remain with power kilogram power minus 1. So it's Newton meter kilogram power minus 1. Newton meter is joule, so it will be joule kilogram minus 1. Okay, so if you want to elaborate on how do we got this formula is, we know the formula gm by r, we'll put the unit. Okay, I hope it clarifies the doubt. Yes. Okay, then what do we have here? The satellite in B is moved to an orbit which the satellite remains at the same point above. Okay, so meaning that it remains at the same point above the planet, meaning it's a geostationary satellite. So okay, the orbit has period of 25 hours. What can be deduced from this about the rotation of Mars on its axis? If geostationary means the planet and the satellite both should have same orbit. So the Mars also has same orbit, meaning Mars rotates every 25 hours on its axis. Okay, state one other feature of this orbit. So this is a equatorial orbit. It will orbit from west to east, east to west. Yes, so it will orbit parallel to the equator of the rotation of the planet, whatever it is. Yeah, that's it. Second question, a helium atom may be modeled as a nucleus surrounded by two electrons in diametrically opposite circular orbits, each of radius 170 picometer. Pico is 10 power minus 12, 10 power minus 12 as shown in figure. Okay, yeah. Okay, state Coulomb's law. I think we know Coulomb's law, directly proportional to the product of their charges and inversely proportional to the square of the distance of their separation. Okay, so state the charge on the nucleus in helium nucleus. In helium nucleus we have 2 proton and 2 neutron. 2 neutron doesn't have any charge, so only its charge of 2 proton, so it will be plus 2e. This plus is very important. Okay, so that the electric force between the nucleus and one of the electron is 1.6 into 10 power minus 8 Newton. Okay, we know the formula for force is 1 by 4 pi epsilon naught q1 q2 divided by r square. Here q1 is single electron, q2 is nucleus, which is 2e. So E into 2e divided by r square. R is the distance between them, which is 170 into 10 power minus 12 meter. Okay, so since it's E multiplied by 2e, we can write 2e square. 1 by 4 pi epsilon naught 2e square divided by r square. So this, in the formula sheet, epsilon naught value is also given, 1 by 4 pi epsilon naught value is also given. So we can directly take 1 by 4 pi epsilon naught value as 8.99 into 10 power 9. And E is elementary charge value, 1.6 into 10 power minus 19. Please don't forget to put the square. So yeah, 170 distance square, 170 into 10 power minus 12 square. So we get 1.59 into 10 power minus 8, approximately 1.6 Newton, 10 power minus 8 Newton. Okay, assume that the force in B2 is the only force on the electron. Calculate speed of the orbiting electron. Okay, so we know that how to find speed in a circular motion, because force is given as a centripetal force. So centripetal force is mv square by r. So this force is given by 1.6 into 10 power minus 8 Newton. So if we rewrite this equation for v, it will be F equal to mv square by r. So v square will be fr divided by m. V will be square root of fr divided by m. F is the force, we found it in last question. So yeah, this is the equation. And m is mass of the electron. So this again you can find it from the data sheet, 9.11 into 10 power minus 31 kilogram. So if we do this, we'll get yeah, so 2.98 into 10 power 12 meter square per second square. Velocity is 1.73 into 10 power 6 meter per second. Okay. Calculate the period of the orbit of the electrons. Okay, we know the velocity. From the velocity we can find the period. We know that velocity is total distance divided by time taken, which is nothing but 2 pi r divided by t. So we want t, we can rewrite this for t. So 2 into pi into 217 to 10 power minus 12 meter divided by 1.72, which is velocity. It's supposed to be 1.73, but it's fine. 10 power 6 meter per second. So t is 6.21 into 10 power minus 16 second. That should do. I'll check the answer if it's right. Yeah. Okay. Okay. In practice, the orbit of each electron is affected by the presence of the other electron. For the position of one of the electrons, determine the ratio of electric field strength due to the other electron divided by electric field strength due to the nucleus. Okay. So let's consider one electron's position. Here is the nucleus and here is the other electron. So distance between one electron and nucleus is r. Distance between one electron and the other electron is 2r. It's a diameter. So to the nucleus r, to the other electron is 2r. Okay. So in this position, what is the field strength due to this electron and what is the field strength due to this nucleus? This is what the ratio. This is what we are finding. We know the electric field strength formula, 1 by 4 pi epsilon naught q divided by r square in that position. For other electron, q is just E. For the nucleus, it's 2E. So we need the ratio. So we will write like this. Electric field strength due to the other electron is, what is the distance? 2r. So it's 2r square. 1 by 4 pi epsilon naught E into 2r square. Remember, it's 2r the whole square, not 2r square. Okay. Electric field strength due to nucleus is, charge is 2E divided by distance is r. So r square. Okay. So we can cancel out 1 by 4 pi epsilon naught and 1 by 4 pi epsilon naught. E and E, r square. Actually 2r square we can write it as 4r square. Okay. Now we can cancel out r square and r square also. So it will be 1 by 4 into 2. So it's 1 by 8, which is 0.125. You can round it off to 0.13. Yeah. Theoretically, we do not even need to substitute the values for r because they are going to cancel out anyway. Nice. Is your answer in D1 to suggest and explain how the orbit of the electron is affected by the presence of the other electron? The idea is, let's say that it's only nucleus and this one electron, so force will be higher because they both are attractive. But if there is other electron, this electron will provide a repulsive force. So it will have less force. Less force means less centripetal force. So mv square by r is less. So less force means less velocity. So less orbital velocity. Less orbital velocity means more speed. More period time. So it will take more time to complete one orbit. So that's the idea. Yeah. Okay. Next. Okay, third question. Define specific latent heat. We know the definition. So specific latent heat is the amount of energy required to change the unit mass state from one state to another state without changing the temperature. Explain why for a substance the specific latent heat of vaporization is usually greater than the specific latent heat of fusion. Okay. So what is specific latent heat of fusion? Energy required to melt from solid to liquid. What's the change between solid and liquid? Distance between the molecules increases by small amount. What is specific latent heat of vaporization? From liquid to gas, the distance between the molecules increase greatly. So you need more energy to increase from liquid to gas than solid to liquid. So that's what they are asking. This is the reason. Vaporization takes more energy than fusion. So temperature is not changing. So the kinetic energy is going to remain change. Only change is potential energy. Okay. So the change in separation of molecule, what is potential energy? Distance between them. Yeah. Okay. An ice cube of mass 37 gram at a temperature 0.0 degree Celsius is placed in a beaker containing water of mass 208 gram at temperature 20. Okay. So we have ice cube whose mass is 37 gram, temperature 0 degree. And we have water, initially its mass is 208 gram and temperature is 26.4 degree. So if you mix together, what will happen? Ice will gain temperature and melt, become water, and water will slightly lose temperature. Okay. So after they reach thermal equilibrium, temperature is 10.3 degrees Celsius. Specific heat capacity of water. Remember, specific heat capacity of water, ice, all are same. 4.18 joule gram per degree Celsius. Okay. Okay. Beaker has negligible. Determine the value to 3 significant figure what specific latent heat of fusion of water. Okay. Now 3 energies are involved. Which has higher energy? Initially, the 208 gram of water at 26.4 degree has higher energy. This energy is utilized to melt the ice and increase the temperature of the water. That water from the melt ice. Okay, molten ice. Yes. So energy of the water is energy of ice melting plus energy of increasing temperature of that water. Water melted from ice. Okay. So how much energy initially the water possesses? 208 gram of water at temperature to 26.4 degrees Celsius. So from 26.4 degrees Celsius to 10.3 degrees Celsius. So we know that the formula E equal to mc delta theta. Here delta theta is from 26.4 degree to 10.3 degree. And we know the specific heat is heat capacity of the water is 4.18. Okay. So this is the energy water of 208 gram provided. Nearly 14,000 joules. Yes. Okay. Let's keep it that way. Now, how much energy is utilized to increase the ice would have melt to water, right? That water is now at 0 degrees Celsius, but it will increase to 10.3 degrees Celsius. So how much? Again, we'll use the same equation, mc delta theta. Now, 37 gram ice melt to 37 gram of water. So 37 into 4.18 specific heat capacity of water. Difference in temperature is 10.3 minus 0. So the 0 degree ice have melted into 0 degree Celsius water. The 0 degree Celsius water's temperature has increased to 10.3 degrees Celsius. The energy utilized is 1592. Okay. Now, how much energy is utilized to melt the ices? We know that this is specific latent heat of fusion. Okay. So E equal to ml. This L only we have to find. We know that M is 37 gram. So let's put, okay, E energy of ice melting is ml fusion. Okay. So 37 into LF representing latent heat of fusion. Okay. Let's put everything in the equation. Energy that water gives is energy to melt the ice plus energy to increase the melt ice water to 10.3 degrees Celsius. So if we rewrite this equation for LF, then we get this. And answer is, I think, 335 joule per gram. Yeah, that's the answer. Next question. Okay. Said what is meant by internal energy of the system. So this we know, I think, from childhood. Potential energy plus kinetic energy of random motion of particles. Yes, okay. Explain why the internal energy of ideal gas is directly proportional to the thermodynamic temperature of the gas. Remember, it's an ideal gas. We are going to write exactly what opposite to what we have wrote earlier. In the ideal gas, no intermolecular force, so potential energy is 0. So all the internal energy is only kinetic energy. Since kinetic energy directly proportional to temperature, the internal energy also directly proportional to temperature. That's all. 3 points. Okay, good to go. Yeah. A sample of ideal gas at thermodynamic temperature T has internal energy U. The gas is compressed so that its temperature increased to 3T. During this compression, the W is done on the gas. The gas is then cooled at constant volume, so its temperature is decreased to 2T. But no change in volume, so work done will be 0 in this one. Okay. Complete the table in terms of W, T and U. Some or all of, okay, work done on the gas. Okay, so first we have compression stage. In compression, initial temperature is T, final temperature is 3T. Okay, so before that, the equation is change in internal energy is heat supplied plus work done. Okay, we know this equation. And thermal energy, we just have to rewrite this equation. Thermal energy supplied to gas is delta U minus W. Okay, we are good to go. Work done is pressure into change in volume. Yeah. Okay, let's look at the compression first. Increase in internal energy is the initial temperature is T, final temperature is 3T. So it has increased plus 2T. Since temperature is proportional to internal energy has increased to 2U. Okay, remember T to 3T, so difference is 2T, so internal energy also 2U. Okay, if internal energy is 2U, work done is W, then delta U is just rewrite the equation. Q equal to delta U minus W. So delta U is 2U, W is W, so 2U minus W. So that's the thermal energy supplied to the gas. Okay, super. In cooling, change in volume is 0. So work done is 0. Then initial temperature is 3T, final temperature is 2T. So change in internal energy is just T, which means it has decreased by T. So it's minus U. From 3U to 2U, so it's minus U. Okay. So if you rewrite this equation, thermal energy supplied to the gas is delta U minus W. Delta U here is minus U. W is 0. So minus U minus W, which is 0, minus U. So yeah, it's minus U minus 0, which is just minus U. Yes. Okay. I hope it's clear. Super. A cuboidal block floats in a liquid with its base horizontal as shown in figure 5.1. Okay, base of the block is at depth h below the surface of the liquid. The block is displaced downwards by a small distance, then released it so that it oscillates. 5.2 shows the variation h of the acceleration a of the block. Okay. Now this is a acceleration versus height graph. Height is displacement in this case. Okay. Figure 5.3 shows the variation with h of kinetic energy of the block. Okay. So we have two graphs. One is acceleration versus displacement graph. Another one is kinetic energy versus displacement graph. Okay, what's the question? Determine the amplitude of the oscillations. Okay, we have the graph here, amplitude, acceleration versus displacement. I think from this we know that where it crosses the displacement, that's the mean position. So in this case it's 1.4. From 1.4 maximum amplitude is, you can take either 0.8 or 2. Anyway, the difference is only amplitude of the oscillation. So 1.4 minus 0.8, which is 0.6 meter. Okay. What the line in figure 5.2 shows? Okay. See, we can see that the gradient is a linear gradient and it has negative gradient. So we can tell it's a simple harmonic motion. So it's a simple harmonic motion. Okay. Next question. State 3 other quantitative conclusions that can be drawn from figure 5.2 and 5.3 about the block and its oscillations. Use the space for error. Okay. Let's go back to those graphs. We'll see. Okay, we need to get some conclusions from this graph. First, let's look at acceleration versus displacement graph. We can see the mean position is 1.4 centimeter. Okay, so let's find the gradient from this graph, which is, we know that the gradient from this graph is minus omega square. So we'll take 2 points in both end, 0.8 comma 0.9 and 2.0 and minus 0.9. So we'll take x1 y1 and x2 y2. We know that the gradient is minus omega square. We'll find the gradient from this graph, y2 minus y1 divided by x2 minus x1. So which will be minus 1.5 second square. So if minus omega square is minus 1.5, then omega is just minus and minus will cancel. Square root of 1.5, which is 1.22 second. Super. So we got angular frequency 1.22. We got mean position 1.4 centimeter. Two informations. Okay. Now let's look at the second graph, kinetic energy. So we know that if it oscillates like this, the maximum velocity will be in the mean position. So there potential energy is 0, only kinetic energy. So in the mean position, total energy is only kinetic energy. So we can understand in mean position, kinetic energy is the total energy. So total energy of the system is 9 joule. So we got three information: mean position, angular frequency and total energy. Okay, let's write those values. So we know the angular frequency. We also know that angular frequency is 2 pi f. So from this we can find the frequency 0.19 hertz. Okay. Also, we know that Vmax, maximum velocity, is omega x naught. We know the omega 1.22. We also know the x naught. So we can work out the maximum. X naught is nothing but amplitude, maximum amplitude. So 1.22 into 0.6, so 0.73 meter per second. We also know the total energy of the oscillation is half m omega square x naught square. So from this we can work out mass of the block. Okay, let's rewrite this equation for mass: 2e divided by omega square x naught square. So we know the total energy is 9 joule. Omega square is 1.5 into x naught square is 0.6 square. So it's 33 kg. Okay, let's write all the points. Equilibrium position of the block is 1.4 meter. Total energy of the system oscillation is 9 joule. Angular frequency of the oscillation is 1.2 rad per second. Frequency of the oscillation is 0.19 hertz. And if you do 1 divided by frequency, then you will get the time period. So 5.1 second. Maximum speed of the block is 0.73 meter per second. Mass of the block is 33 kg. Remember, sir, in marking scheme, the angular frequency value, the frequency of oscillation value and the time period value, all three together contains 1 mark. So if you give any one of this, 1 mark. If you give all also, you will get only 1 mark. So find the relevancy in the answer. Okay, super. On figure 5.4, sketch the variation with h of the potential energy EP of the oscillation. Okay. So first we know that the total energy is 9 joule. So let's draw a line 9 joule. And we know the mean position is 1.4 centimeter. In mean position, total energy is only the kinetic energy. So potential energy will be 0. Okay. And let's mark the both end 0.8 and 2. Where in both end potential energy will be maximum. Kinetic energy is 0. So total energy is only potential energy. So if we connect these 3 dots, we get the curve. Good to go. Yes. Okay. In figure on it, check if we miss anything. I don't think we miss anything. Yeah, it looked like a dead end question. Yeah. Okay. In figure 6.4 shows a circuit that rectifies an alternating input voltage and produces an output voltage across a resistor R. The 4 terminals of the rectification circuit are labeled W, X, Y and Z. A capacitor C is connected in parallel with resistor R. Okay, what's the question? State what is mean by rectification. We know rectification is converting AC to DC. State the purpose of the capacitor. Purpose of the capacitor is to smoothing. Okay. Figure 6.2 shows the variation with time t of the potential difference as V in and V out. Okay, so V in is a dotted line. We can see that it's a AC, and V out is the continuous line. So we can see that it's been smoothed out. Okay, super. In the variation of V in with T can be represented by, the variation of V in with T can be represented by V in equal to A cos Bt, where A and B are constants. Determine the values of A and B, give a unit with your answer. Okay, so in the general equation, this is a sinusoidal equation, A cos Bt. Okay, so A is the amplitude, total amplitude, the maximum amplitude, and B is the angular frequency. Okay, so we need to find amplitude and angular frequency. So we can look at the graph. Easily we can tell the amplitude is 12 volt. Okay, whatever the unit in the y-axis, that's a unit of the amplitude, so it's 12 volt. Okay, now let's look at the time period. To find the angular frequency, we cannot find the angular frequency directly from the graph, but we can find the time period. From the time period we can find the angular frequency. So we'll take 2 points from full cycle. I have took 25 and 05, so 20 milliseconds. We should not forget the milli. So t is 20 millisecond. We know that omega equal to 2 pi divided by t. So omega will be 2 pi divided by 20 into 10 power minus 3. So 314 rad per second. Yeah. Okay, 2 mark. Determine the type of rectification produced by the circuit. It's a full wave rectification. Okay, because two terminals are there, two output terminals are there, and capacitor is used to smooth out. So full wave rectifier, full wave rectification. Okay, on figure 6.3, draw the circuit diagram for the components inside the rectification circuit. Okay, so our objective is this: between W and X, positive and negative will oscillate, but Y and Z, Y should be always positive, Z should be always negative. Okay, let's say that in W, first it's positive, so it should goes like this. Okay, remember the diode is in forward bias. What if it is negative? Then the negative should go to the Z, right? So we'll put in a diode reverse, so it will go to Z, negative. Now in X, if it is positive, it should go to the Y, so it will go like this. If it's negative, then it go to the Z, so it will go like this. Tada, we have a full wave rectifier. Okay, so you can draw in any way you like. The idea is positive should be always Y, negative should be always Z. That's all. Okay. Determine a value for the time constant for the discharge of the capacitor C through the resistor R in figure 6.1. Okay, so actually we need to take a look at the graph. So I forgot to connect the graph. Okay, from the graph, if you see, we can see that it's been smoothed out between 8 and 12 volt. Okay, and time also we can see. The time taken for discharging the graph is actually from 0 to 7.3. Okay, it's actually, you can take value from 7.1 to 7.3. Okay, what equation we can use? We know that V equal to V naught e power minus t by tau. T is the time taken, tau is the time constant. Okay, now we have to find the time constant tau. So let's rewrite this equation: minus t divided by log, it is actually log base e, so it should be ln, not log, V divided by V naught. And from the graph we know that t for discharging from here to here, so it's 7.3 millisecond. So you can take any value between 7.1 to 7.4, it should work. Okay, So V naught, the original voltage is 12 volt, and V, the final voltage is 8 volt, discharged voltage. So if you put these things, we should put, so the minus is from the formula 7.3 into 10 power minus 3 second divided by log base E 8 divided by 12, so which is 0.018 seconds. Yeah. Okay. The capacitor C has a capacitance of 570 microfarad. Use answer to determine the resistance of the resistor. We know the time constant is R into C. So we just have to rewrite for R. So it will be 0.018 divided by 570 into 10 power minus 6. So resistance will be 32 ohm. Yeah, 31.5 ohm. It's fine. Define magnetic flux density. Okay, we know that F equal to BAL, so B equal to F divided by L. So magnetic flux density is force per unit length per unit current on a wire placed right angle to the magnetic field. Why right angle? Sine 90 degrees one. Okay, blah blah blah. Yes. Okay, a particle of mass m and charge plus q, so it's a positive charge, moves at a speed v into a region where there is a uniform magnetic field. Okay, so its magnetic field is going into the page, particle is going from left to right. Okay. Okay, state an expression in terms of r. Okay, mqv and v for the magnetic force. We know that F is bqv sin theta. In this case it's perpendicular. Okay, velocity of the particle is in this direction, magnetic field is in this direction, so they both are perpendicular. Okay, so sin theta is 90 degrees, so it will be bqv. Okay, on figure 7.1, draw an arrow at point y to indicate the direction of the force in B1. So as it enter the point y, so it's actually current is given, force is asked. So it's a motor rule or left hand rule. So the particle is in this direction, so velocity is in this direction, magnetic field is going in this direction. Okay. Yeah, so the index finger for field, it's going inside, so the second finger for current, it's going from left to right, so it will experience a force in this direction, upward. So it's a left hand rule. So initially the at y particle will feel the force upward, left hand rule. As it goes, it will just make a trajectory, so it will go in a curve. That's 3. On figure 7, draw a line to show the possible for, so it will just it has to curve as it, and it will circle. Okay, as long as it stays in the same velocity, it will circle. Okay, super. Explain how the electric field can be used with the magnetic field to ensure that the particle B now passes through its point set. Point set is in the other direction, so if it want to pass through, it should go undeviated. Okay, now let's say this is the point y. Now we have, if it enters from the left to right, then we have magnetic force, upward force. Okay, now let's say that we introduce electric plates, positive and negative, up and down. Okay, so now it will have a field line from top to bottom. So now the particle will experience electric downward force because particle is a positive charge, so it will move towards the negative plate, it will be repelled from the positive, so it will have net downward force. So when the magnetic upward force is equal to electric downward force, it will not go in a curved path, the forces are balanced due to electric and magnetic, so it will go straight line. So let's put in the writing. Magnetic field gives an upward force for the positive charge. we can set electric field with positive terminal at the top and negative terminal bottom of the page, so that field line is from top to bottom. So the positive will move from top to bottom. So when both forces are equal, the resultant force is 0, so the particle's velocity goes undeviated. Okay, derive an expression V in terms of B and electric field strength E. Okay, so force of magnetic particles, the force experienced by particle due to magnetic field must be equal to force experienced by electric particle by electric field. Okay, so force experienced by magnetic is BQV, force experienced by electric is EQ. E is the electric field due to the charge, okay, field. Yeah, now Q and Q can cancel, so BV equal to E. If you rewrite V, it's B divided by, E divided by B. Done. What is mean by de Broglie wavelength? Yeah, it's wavelength associated with the moving particle. Okay. Calculate the de Broglie wavelength of an electron moving at a speed of 4.9 into 10 power 7 meter per second. We know that de Broglie wavelength is h by p, where p is momentum, so mass of the electron into velocity. So if you put it in the equation, mass of the electron is 9.11 into 10 power minus 31. Planck constant is 6.636 into 10 power minus 34 kilogram meter square per second inverse. So if we do the math, then we'll get wavelength of 1.48 into 10 power minus 11 meter. Okay. State one similarity and one difference between an electron and a positron. So both are fundamental particles, electron and positron. So both are lepton. They have same magnitude of charge. They have same mass. So this is a similarity. What's the difference? Electron is let's say particle, and positron is antiparticle of electron. So electron is negative, positron is positive. Okay, their charge is just E. Okay, an electron moving at a speed of 4.9 into 10 power 7 meter per second collides with a positron that is traveling at the same speed in opposite direction. As a result of the collision, two gamma ray photons are produced. State the name of this type of reaction. So it's called annihilation. Particle and antiparticle join together and form a pure energy. Their mass is converted into energy. State what happens to the electron and to the positron. Yeah, so as we said, they just meet together. Their mass is converted into pure energy. That's gamma ray of photons. Oh, sorry, I gave this answer. Okay, so explain why two gamma ray photons. If just one gamma ray ejected, it will go in this direction. So something must go backward, right? If it goes this direction, something must go in this direction, backward. So if two protons, it's all the masses converting energy. So to conserve the momentum, only two protons travel in opposite direction, so momentum is conserved. Instead of one photon taking all the energy, two photons taking half of the energy each. Clever idea. So that the kinetic energy of the electron before collision is 1.1 into 10 power minus 15 joule. So we know kinetic energy is half mv square, we know mass of the electron, we know the velocity 4.9 into 10 power second. So if we do this, then we'll get 1.09 into 10 power minus 11 joule, 15 joule. So 1.1 into 10 power minus 15 joule, rounding off. Okay. Use the information to determine to three significant figure the wavelength associated with gamma radiation emitted in the collision. Okay. So here is where most people will make mistake. They just take the kinetic energy, and we know that E equal to hc by lambda. If you do not know, E equal to actually hf and F equal to c by lambda. So E equal to hc by lambda. Most people just take the kinetic energy and equate to hc by lambda and get the wavelength. But problem is, it's not kinetic energy alone. Remember, both the masses, they turn into pure energy. So energy associated with mass also we have to include. which is E equal to mc square. Okay. Now we are figuring out only wavelength of gamma radiation. Okay, so only one wavelength of one gamma. So we do not need to use the two. So you take one electron. What is the kinetic energy of the electron, and what is the mass energy equivalence of that electron? That energy you should take to find the wavelength of the photon. Okay. So energy total is kinetic energy plus mc square. So we know that kinetic energy is, we just found okay, kinetic energy we found lastly, I think we found it as kinetic energy, we just found it as 1.1 into 10 power minus 15 joule. Let's find out the mass energy equivalence of the electron, E equal to mc square. So m is 9.1 into 10 power minus 31. C is velocity of light, so c square 3 into 10 power 8 square. So the energy is 8.19 into 10 power minus 14 joule. So total energy is kinetic energy plus this energy. So 1.1 into 10 power minus 15 plus 8.19 into 10 power minus 14. So total is 8.31 into 10 power minus 14 joule. Okay. Remember, the E equal to mc square is higher, kinetic energy is lower. Okay. So let's now substitute E equal to hc by lambda, rewrite the equation for lambda. So lambda equal to hc by E, h is Planck constant, c is velocity, E is energy we just found. Yeah. So few people also ask where to use electron volt and where to use joule. If you are finding wavelength, energy is given in joule, you can directly use. If energy is given in electron volt, then you have to convert that electron volt into joule. Okay. Super. Define activity of a radioactive sample. So it's number of nuclear disintegrations per unit time. We know that. Okay. Explain why the variation with the time of the activity of an radioactive sample is exponential in nature. Okay. So any function that the variable is directly proportional to change in variable, then it will follow a exponential curve. For example, I have x, this is I have a dx, change in x, which is directly proportional to x, then it will follow exponential decay. This is the idea. Okay. So how in physics we are going to tell that the variation with the time of the activity of a radioactive sample is exponential decay is, let's take two equations. One, activity is lambda into n. So activity is proportional to number of undecayed nuclei. N is undecayed nuclei. Since lambda is a constant, A is proportional to n. Then we have one more equation. A is also proportional to delta n by delta t. Okay, minus. So activity is proportional to the rate of change of number of. So you can see activity is proportional to n. Also activity is proportional to change in n. So n is proportional to change in n. Hence it's exponential. That's all. Okay. So where the change is proportional to the original number, then it is exponential. That's the idea. Okay. Sample contains a single radioactive isotope that decays to form a stable isotope. Sample has activity of 180 becquerel at the time t equal to 0. At 8.4 minutes later, activity is 120 becquerel. Determine the decay constant in minute inverse of the radioactive isotope. Okay. We know we have to use the formula n equal to n naught e power minus lambda t. So we have to find the decay constant, which is lambda. So let's rewrite this one, n by n naught minus t. Okay. So n is the present value, what's activity after 8.4 minutes, t equal to 8.4 minute, n is 120 becquerel, original value of n naught is 180 becquerel. Remember in the previous question we used 12 and 18, now we are using 120 and 180. See, interesting. Okay. So it will be log base E of ln 120 by 180 is minus 0.405 divided by 8.4, which is 0.048 per minute. So the decay constant is 0.048 per minute. Okay. Is your answer to determine half life. We know this T half is log by C 2 divided by lambda. So ln 2. We know ln 2 value is 0.693 divided by 0.048, which is 14.4 minute. Okay. On figure 9.1, sketch the variation of the activity A of the sample with T for values of T between T equal to 0 and T equal to 24 minute. Okay. So we have already in the question it's given at T equal to 0 activity is 180. Okay. So we can mark this point. And at T equal to 8.4 activity is 120. So we can mark this point also. Sorry, 8.4 minute, 120. And we figure out half-life is 14.4. So after half-life, original activity is 180 divided by 2, which is 90. So if we connect 3 dots, then we get an exponential curve. That's all. Okay. State Hubble's law. Speed of recession of a galaxy from an observer is proportional to distance from observer, blah blah blah. Yeah. I think H equal to V naught by T. Is it so? Yeah, whatever it is. Yes. Okay. Star in distant galaxy emits radiation that has maximum intensity. Observation. Okay. Explain why the observed wavelength and emitted wavelength have different values. Because the galaxy is moving away from the observer, so the whatever wavelength we see, the apparent wavelength will be bigger than the actual wavelength. So the wavelength has increased, which is redshift. So galaxy is receding from Earth. It should be receding. So autocorrect receiving. Oh, sorry about that. Okay. So the observed wavelength will be longer than the actual wavelength because of the redshift. 2 marks. Okay. Okay. Calculate the speed of the star relative to the Earth. We know that this formula V by C is delta lambda by lambda. So ratio of velocity to speed of light is equal to change in wavelength divided by actual wavelength. So we know that we can rewrite this for V. We know that the change in wavelength is 4.91, which we receive, 4.62, which is actual. So 3 into 10 power 8 for C, delta lambda is 4.91 minus 4.62 into 10 power minus 7 divided by actual wavelength is 4.62 into 10 power minus 7. So I can cancel out and then we'll get 1.88 into 10 power 7 meter per second. Oh. Okay. The wavelength of maximum intensity of emission is used to determine the value for the surface temperature of a star. Explain how the temperature determined using the observed wavelength compares with the true value of the temperature determined using the emitted wavelength. Okay. How do we find the temperature actually? We know that the lambda maximum intensity of emission, the wavelength of maximum intensity of emission is proportional to 1 by T. This is how we will find. So if lambda max, if we use the actual wavelength, then we will get the exact temperature. But if we use the observed wavelength, the lambda is higher, so T will be lower. Okay? Yes. A value for the Hubble constant is 2.3 into 10 power minus 18 second inverse. Use your answer in B2 to determine the distance of the star. We know that H naught equal to V by D. So if we rewrite for D, then V by H naught. So 1.88 into 10 power 7 divided by 2.3 into 10 power minus 18. So D should be 8.2 into 10 power 24 meter. Super. Okay, what's correct?